I'd like to introduce our final speaker today. That's Rommel Carvalho. Rommel's a graduate research assistant and a PhD student at George Mason University. He's going to tell us today about PROGNOS. Rommel.
Hi there. We're going to talk about the Predictive Situational Awareness with Probabilistic Ontologies. This is part of the PROGNOS project supported by ONR and developed by George Mason University. So the agenda today is going to be, I'm going to talk about the broad objective we have on this project, methodology we're following to develop those ontologies, how we're going to model those probabilistic ontologies for the maritime domain awareness, talking about coming up with the requirements, analysis and design, and implementation of those models. Then we're going to talk a little bit about how we use those models to come up with the reasoning process, and then, of course, how we're going to develop the framework to test all that, and draw some conclusions about it. So as the objective goes, we want to develop, of course, probabilistic ontology capable of reasoning with a lot of evidence, masses of evidence coming from different domains and also different sources to provide situational awareness in this domain we're talking about. This is part of the project that I talked about, PROGNOS, the Probabilistic Ontologies for Net-Centric Operation Systems. And we're going to use things like probabilistic ontologies, as PROGNOS is a language that extends our language. I'm going to use MIBN logic that extends Bayesian networks to be more expressive. High-level fusion and UNB-Bayes, which is an open source tool that works with probabilistic reasoning. Although I'm not going to go into detail on those things because it would take me much more than the time I have. So as far as the methodology goes, we first want to come up with the model. And trying to find, there you go. And the first thing we want to work on is, okay, what are the requirements? What are we looking for? What are the assumptions and what we're trying to do? Then we can do some further analysis and design and finally the implementation depending on the language you're going to use. But also after you have that model, what you want to do is actually you want to populate your knowledge base, and you could say that this is the A box part of it where you're going to enter the instance and all the findings that you have. And here on the bottom, you're going to do some reasonings where the user is going to say, okay, these are the queries I want to know. Do I have any threat going on this place, or which ship should I board on, or so on and so forth. And then on our specific case, where we're using MIBN and PROGNOS, we're going to create some situation-specific Bayesian network to do the inference for us. So this is kind of a dynamic Bayesian network where we're going to create a specific Bayesian network for a specific context. So it really changes depending on what you have on your knowledge base. And to do that, we have this probabilistic ontology modeling cycle, where in blue you see the requirement phases, analysis and design here in green, and they're all language independent. And then you have the implementation part where you actually have something independent, in our case, to PROGNOS and MIBN. So we start, the main thing we're looking at, so what are our goals? And on that goal, what are the kind of query we're going to expect from the users, right? And to answer those queries, how am I going to, which kind of evidence do I have to look for? Which kind of observables, as someone else here was talking about? So those are the main things we have to start looking at. Then we can think about what's probabilistic ontologies and so on and so forth. So after we have this, we can come up with the entities we're going to have, the attributes, the relationships, and after that, you can actually say, okay, what are the rules behind this? What are the deterministic rules and the probabilistic rules? After you have that, you can actually go and implement and map that to MIBN fragments, and I'm going to just show a little bit of that as we go through. So for the requirement, and I'm going to go through this here, this was done with a subjective matter expert. So it's not something based on statistical, data that we collect or anything like that. So we do have those things like the probability of having a terrorist is 0.05 or something. It's not really the thing that we know for sure, but it's just a subject matter expert idea. So the main idea, the main goal here, I didn't put here, but the main goal is to find a ship of interest. And a ship of interest is, we're on the sea and we have this, hundreds of thousands of, hundreds of ships around us. And you're trying to see, okay, which one presents a threat? Which one should we board? So what are the kinds of questions we should be asking to know if that ship is a ship of interest or not. So some of them are, oh, does the ship have a terrorist crew member inside, associated to it? So how do we come up with an answer to that? So ideas to do that is verify if the crew member is related to any terrorist. So look at the social network of the people that you know it's on that ship and see if it's related to any terrorist or maybe to a terrorist organization. Another question that you might ask is, okay, is he going an unusual route? Because he said he's going from point A to point B, but he's going through this other, going all the way south to then go north again. So why is that? You might find that pattern there. So we kind of have a black box inside the simulation tool. I'm going to talk a little bit later. And we have ways to find that. So we're going to receive those information as reports. And the same thing for meeting behavior. So usually you might have a big ship meeting a smaller ship to transfer some illicit cargo. And from that, we also are going to assume that they're probably doing something wrong. Another thing is presenting evasive behavior. So is this ship presenting some kind of strange behavior? And how do we capture that? Trying to find some ECM being used, or maybe he's not being responsive on the radar or something else, right? So those are the main things we're going to talk about. And to do that, we first come up with a lightweight ontology where we have all the entities and attributes and the things we talk about. That is the next step. So we have things like ship, position, meeting, and you have a person, could be a terrorist, and there's a crew member, and so on and so forth. With that in mind, we try to group those entities in fragments, and we're going to understand why we do that later. But trying to say, okay, this is related to electronic stuff, this is related to behavior, this is just information for the ship, and so on and so forth. After you do that, we can think about, okay, we have those questions, so what are the probabilistic rules associated to those evidence we're collecting and the questions we try to answer? And you can think of it as a hypothesis we're looking for. So, a ship is, in our assumption, of course, we say that a ship is a ship of interest if and only if it has a terrorist crew member associated to it. So it's only going to carry, some illicit cargo. Probably going to have somebody inside there that knows the illicit cargo is there. So we assume that we're going to have a terrorist inside. That's not to say that we know that this guy's a terrorist, but he's there. And we go on with a lot of other probabilistic rules, and I'm not going to go through all of them, but I'm just going to show a little bit of what we have. Maybe if a crew member is related to a terrorist, then it's more likely that he's also a terrorist. And the same thing goes for the organization. If he's associated to a terrorist organization, it's more likely that he is a terrorist. But it might not be the case, right? So we go on with other rules based on those questions and those evidence that I just showed you in a few slides back. And so, a ship of interest is more likely to meet other ships for trading illicit cargo. But again, as a background in another presentation we had, it might be just the case that they're, they pass through close to each other, and we might think that they're meeting, but they're not really meeting. And we go on with all these different rules. If it's ship of interest, it's more likely that it's going to have evasive behavior, and if it's a evasive behavior, it's more likely to have this other observable, and so on and so forth. And we translate those rules to what we call Migman fragments. And those Migman fragments, they pretty much have three components. One is the context node. The context node pretty much tell you what's the criteria that has to be true in order for this relation to also be true, right? So the only one we have here is, okay, the variable ship has to be a ship, the type ship, right? And we have that, remember we talked about, it's only a ship of interest if it has a terrorist crew member. So we show that on a local probability distribution where it has parents and children. The resident node is where you're going to define your local probability distribution. It's pretty related to the conditional probability table that we have in Bayesian networks. And the input node, it's only a resident node, this guy here, that has the local probability distribution defined on another mfrag. So that's why we divide it in fragments, as I talked before, the entities, trying to find them as groups. So here we're trying to simulate, we're trying to model everything we showed on those probability rules we have defined. So if he's related to another person that is a terrorist, then it's more likely he's going to be a terrorist. And if he's a terrorist and he's part of an organization, it's more likely that organization is a terrorist organization, and so on and so forth. With all the different, and if you come up with a new rule, then you can create this new fragment. and it's kind of easy to plug in as you add more rules to it. And the good part of it is when you create you do the reasoning, it's just going to instantiate and use the parts that are relevant to the context you're working with. So although you might have thousands of evidence and hypotheses you want to test, it's just going to instantiate those related to the data that you have. So for instance, the simple example, I just have two information that, I know this person, one is related to a terrorist, and maybe this, I know this guy is also the crew member of ship 1, right? So I know the probability of that he is a ship of interest, so it's 70%. So I can play around, I can also change the values here. It might be the case that I'm not sure it's 100%, but I have some kind of black box tool that tells me, oh, it's 75%, and then I put that value there, and I can have different probability associated to that. We did some testing talking about scalability, so how far are we going to be able to go with this? And what we found out with empirical tests, we still have to do some more analytical analysis, but we did see that it seems to be linear to the number of nodes we have on our network. So the more evidence we have, we're going to have more nodes, but it's linear at least with the number of nodes. However, the number of nodes is exponential with the knowledge base size you have. So the more information you have, the more nodes you're going to have. So although it's linear to the nodes is exponential. So it is a problem. So how are we going to deal with that? So we had two approaches for that so far, although we have some other things we're doing. But in this paper, I'm just going to talk about two. And the first one is we implemented, instead of having that huge network that you just saw before, we have a multiply section Bayesian network, and it's a situation-specific multiply section Bayesian network. So we instantiate that, and pretty much what we have here are subnetworks, and those subnetworks you can think as an instance of that fragment. So every instance we have for that fragment that I showed you before is a subnetwork. And what we can do with this is we can explore local computation. So we don't need to take everything into consideration, but just what we're trying to answer. So if my question is here, maybe I just need this fragment to answer my question. It's a lot faster than looking at everything. Of course, another thing we looked at is we need to use approximation algorithms, so implementing things like keep sampling, likelihood weighting, and so on and so forth. So we do have the exact inference. We also have the approximation. Those are the two things we worked on and we showed on this paper. So let's move on to testing. Here I'm going to present the framework we created to do our testing. And pretty much what we do is we're trying to simulate the ground truth, right? So we know it might not be the case that we get information from the Navy telling everything they know about it, but we can do some assumptions and we can generate some ground truth values. So what we have here is that some information are based on some Bayesian network that we use to do forward sampling. So things like what's the probability of a person being a terrorist? Then I sample and I say, okay, this guy's a terrorist. Okay, so we use those kind of things. Of course, you're going to have some other inputs like how many people you want on this simulation, how many ships you're going to have, how many organizations you're going to have on this simulation. Then what we do is we create those guys and we create a social network, so we associate people to other people, and then we're going to know if they're terrorists or not. We create the ships, we associate people to ships, saying that they're crew members, and then of course we simulate the ground truth based on that Bayesian network for all those entities we're creating, right? And those entities, they're actually going to become agents on our simulation tool. So in our simulation tool, we have all the entities created here on the side, and here you can see the ground truth, where we know if it's a ship of interest, we know if the people associated to that ship, and if it's a terrorist or not, and so on and so forth. So what we do with that simulation, and they don't have the running simulation here, but if I press run, the ships have different behaviors based on the ground truth they have. So they have an initial set of ground truth, and then based on that, they're going to have different behaviors. They're going to generate new observables, new evidence, right? So with that, what we do is, well, it would be nice to know the ground truth of everything, right? But we don't. So what we do is we randomly generate data that maybe the CIA would know, and this, of course, is what we created as the CIA database. The FBI would know. But again, these are like, maybe FBI and CIA would know more about the social network part of our model, right? And then that's why I have a different Bayesian nets here. But the Navy would know more about ships and positions and crew members and so on and so forth. So you might have overlapping here, but you probably have information here that you don't have there, and so on for other databases we want to do. And what we want to do is actually grab the data from all those different data sources, combine them, and then create this idea of, okay, this came from FBI, this came from the Navy, and we generate the situation-specific Bayesian network, which gives us an answer to a query we might ask. Okay? So what we want to do eventually is get this posterior probability we computed and compare it to the ground truth we know. So just to make sure, I'm not sure if I mentioned, but I'm not gonna generate a report saying that ship 1 is a ship of interest. So some data are never observable, let's say, at least on our simulation tool. So just to make sure we're not being unfair or cheating on our results. So my question is this equal? And I don't have the equal sign here. I don't know why. But anyway, we're gonna compare the two. The other thing is we might come up with a posterior probability saying, okay, it's a probability of 99% of this guy being correct. However, it might be the case that 99% of the cases you're wrong. So how good is that? It's good for nothing. So knowing just the posterior is not enough. And we have a paper on this from last year's Fusion conference where we talk about computing the probability of correct classification using Bayesian networks. So what we want to do is when we compute this situation-specific Bayesian network, instead of just computing the posterior probability for a question that you pose, we are also going to compute, how often based on this, method we have, are we correct? So we give you both answers. Okay, I'm 75% of the time correct, and I'm 80% sure that it's a ship of interest. Okay, so those are the ideas, and the conclusions are, we show how to use the uncertainty modeling process for the semantic web to create this probabilistic ontology for the maritime domain awareness. We implemented different solutions to scalability. That's not to say that we solved the problem, but we just, tackling the problem in different ways. We did implement a solid framework for testing the model, so you can generate different scenarios, and it's random, it's stochastic, so it's really easy for the user to test and see if the models are doing all right. So we did have the simulation. We have how to compare the results to ground truth. That's not going to happen in the real world cases. And we can also do the probability of correct classification evaluation. For future work, of course, we have to improve our probabilistic model and take into consideration some statistical data we might have. Also improve the scalability, and we are working on a module called hypothesis management, where we remember I talked about the explosion depending on the number of nodes and the size of your knowledge base. Working with hypothesis management, we try to control that number of evidence we're going to work with, or the number of hypotheses I'm going to work with. So this deals a little bit with that, and of course improve communication, because the way we're getting the reports now is just calling the Java library or something. But we're eventually gonna work with web services and ontological web services, and that's the next step we're gonna also work on. And we do have to actually, after we tweak a little bit our agents and make sure they're doing what they're supposed to, we're gonna come up with the comparisons and show some results and some graphs on how well we did. I guess that's it. Thank you very much.
Thank you. Questions for Rommel?
Okay. Did I talk too fast? Okay.
I did a quick one. How do you deal with deception? If I was a terrorist on a vessel about to go to make an attack, and I was already known to the authorities, I doubt I'd be travelling under my own name.
Yeah, that's true. But again, that's why we also depend on reports you might get from different agencies when you're talking about human reports. So, eventually they're going to figure something out like that. He's faking the name and we found this person. It's not supposed to be there. Sometimes they change the name of the ship. Also, you think there's a certain ship and it's actually another one. So there are different ways to tackle that problem. And as I said here, the evidence can become your hypothesis later on as you come up to more detailed information. For example, on the tree example, you have sub-goals and sub-goals, sub-goals. Well, on the first step, it might be the case that you just have a small tree, but as you go on, you want to talk about this observable, you transform that observable into sub-goal, and you have more evidence that gives you more detailed information about that. So, there are different ways to tackle that problem. You can have a black box outside that's a human report telling you, or maybe, you can put that on your Bayesian networks also by getting some different kinds of evidence.
One more, Jim.
Have you done any sensitivity analysis to the correctness of the likelihoods?
No, we haven't done that yet. And pretty much what we've been working so far is implementing those different algorithms, creating this model, and actually creating the framework so we are able to do the testing and do some other analysis and how it's going to vary depending on the distribution we have and you know, when we add some other rules and so on and so forth. So no, we haven't done that yet, but yeah, it's on our next step for the schedule.
Just quickly, have you tried any, because you generate a lot of samples, so have you tried any discriminating models? Like you have the ground truth, you have lots of samples, as opposed to some generating models like Bayesian. Have you tried any discriminating models? Might get a better performance.
No, haven't tried that. I don't know, we have to look at it and see, but no.
Okay, that concludes the session then. Please thank Rommel and all our speakers.